Today we have three presentations from our colleagues at Harvard, from University of Illinois at Urbana-Champaign, and from Notre Dame to share with us very exciting research on AI in education. I also wanted to mention that there is a quick audience poll shown on the slide. At the bottom, there is a link, a tiny URL link to the poll, and also a QR code to scan to access the poll. It will be much appreciated if you could scan that and fill that out. We're going to actually show the results in a few minutes to understand better our audience today. Maybe next slide, please. So today, my name is Allison Chang. I'm a professor in Department of Psychology and the Associate Director of the Lucy Family Institute for Data and Society, and the Fellow of the Institute for Educational Initiatives at the University of Notre Dame. I've had the honor and pleasure to work with my colleague, Dr. Alex Ambrose, also at the University of Notre Dame, who's a professor of practice and affiliated with the Knupp Center for Teaching Excellence of ND Learning and the Institute for Educational Initiatives. Today's symposium is a follow-up to the in-person meeting that we had last December, which attracted nearly 300 participants, both in person and online. And today, 6 months after that event, we're gathering again to see exciting new developments in AI for education. I'd like to thank our sponsors, the Lucy Family Institute for Data Society, Notre Dame Learning, Notre Dame Research, and Institute for Scholarship in the Liberal Arts. Next, my colleague Alex is going to take over and go through some logistics. So.
Thank you, Allison, and hello, everybody. Thank you for all coming today. Just some quick logistics to help make sure we make this as smooth and engaging and interactive as possible, given the numbers. You might have heard and saw that this webinar is being recorded, and we have the closed captioning on available if you would like. We're going to use Zoom's Q&A tool, which allows you to submit questions along the way, and even those viewing the questions can upvote and rank those questions that you want us to focus on the most. So we really encourage you to try to use that tool to submit questions. If it's difficult, you're welcome to go ahead and just use the chat, and Allison and I will be happy to bubble up those questions. So let's take a quick peek at some of the polls that have been coming in so far, just to get a sense of who the audience is, to allow our presenters really to focus and personalize to that. So it looks like we have about 20 responses so far, and we have a nice distribution here of some graduate students, some faculty, and some staff are the three largest groups here. It looks like we have a lot of early adopters and innovators here, and a lot of AI optimists and enthusiasts here. AI literacy, it looks like more than about half are somewhat literate or even fluent, which is great. And it looks like 40% of you are using generative AI tools, up to 40% daily, with weekly coming in next. So thank you for taking a moment to fill that out. We're going to go back to the slide deck and give you the overview. So again, we have 3 sessions lined up here, and each presenter will present for roughly 15 minutes, and then we'll have a good 10 minutes of Q&A through that question and answer tool for each session. So we'll do session 1 with Dr. Young-Won Kim first. With that, I'll pass it over to him so he can begin his presentation.
start the sessions? Okay. Let me share my screen first.
Sure.
Okay. Good afternoon, everyone. It's a pleasure to be here at this symposium. I'm excited to kick off the presentation today by sharing our research titled ChatGPT versus machine learning, assessing in the efficacy of large language models for automated essay scoring. My name is Youngwon Kim, and I had the privilege of collaborating with Drs. Moser, Miratrix, and Al-Aldami on this project. Let's go over the presentation plan for today. First, I will begin with a brief overview of automated essay scoring, then explore the data, measures, method, result of this approach. Finally, I will discuss limitations, future research, and some implications for this research. Sorry. Okay. Can you see it clearly? Sorry. Every essay evaluation is a critical part of education. But if you've ever graded a stack of essays, you know it can be incredibly time-consuming and exhausting. In fact, during my time as a TA in a graduate school, I loved working with the students, but it was challenging for me to grade students' essays again and again and again. Yes, right. The human grading is labor-intensive and time-consuming and potentially susceptible to bias, especially when dealing with a large number of essays or the involvement of multiple assessors. So to address these challenges, automated essay scoring, which is AES, offers a technology-driven solution. But as we let you know, AES is far from simple because the system needs to evaluate not just grammar and spelling, but the overall contents, organization, and the writing quality of an essay. So despite the advancements in AES, the evaluation process still heavily relies on human graders. Completely eliminating human involvement seems impractical in real-world scenarios. Now, let's turn to the promising new direction in automated essay scoring. Moser and Miratrix, they are my collaborator, in their recent study, introduced a hybrid approach that combines the best of both worlds, human expertise and advanced computational techniques. They even developed our package, which is RCT text, to implement this approach. Here is how it works. Step 1, first, by using sophisticated natural language processing tools like Quantita, LIWC, and TACO, this approach automatically analyzes existing essays. It extracts key features related to language patterns, vocabulary, and writing styles. Step 2, Step 2 is next. This machine learning algorithm takes those extracted features and predict potential scores for the essays. These hybrid approaches can grade essays with remarkable accuracy while saving time and reducing bias. This is a very similar approaches used by ETS, E-Rater system, one of the most popular commercial system in AES. Sorry, okay, here. So, and then let's explore another cutting-edge development of large language models, which is LLMs. Machine learning's prediction with the text features don't understand the essays, but large language model, which is ChatGPT, can understand language at a deeper level, much closer to how humans do. Think of it like this. An LLM like ChatGPT are capable of grasping the context and the nuances of of an essay, giving them potential benefits for essay scoring. So research has shown the impressive capability of LLMs in various areas. They excel in analyzing text and determine things like whether it's helpful or harmful and polite or impolite. However, when it comes to the continuous scoring needed for essay scoring, the results haven't been as strong. So this presents a key challenge and an exciting focus on our study. So investigating how to use this power of large language models for more accurate and reliable essay scoring. Importantly, there's limited research directly comparing the performances machine learning models against the large language models in essay scoring. So this gap in knowledge leads us these following research questions: and how well ML grading and LLM grading work for assessing student essay as compared to the human scored gold standard, and which method exhibit superior performance in grading, both for categorical and continuous outcomes. Okay, so our research used the data from CDD study. Specifically, we utilized the word generation components, where the 4th and 8th graders wrote persuasive essays about iPad usage in their schools. And then for the reliable baseline, the 7 research assistants scored and classified all the essays. And then we started with the 3,542 essays and carefully selected 2,687 for in-depth analysis. And next measures, the NIEP holistic writing rubrics was used to assess writing quality, considering 3 criteria such as development ideas, organization, and language facility and conversation. Essay are rated on 7-point scale. And then the opinion classification, which is categorical data. So 5 distinct students' opinions on iPad usage were identified: affirmative, negative, balanced, ambivalent, no argument. But we aggregate balanced, ambivalent, and the argument into a single other category due to low prevalence. So, and then we mainly employed tree-based model for handling features from the text. So models are trained on varying data. Percentages ranges from 5% to 90% to understand how too sensitive our models are to amount of the trained data. And then we used 2 random algorithms and 2 gradient boosting algorithms. And then the ChatGPT, we used ChatGPT 3.5 Turbo, like older one, and then the updated one, but they updated again while we are studying this. But this is kind of old version because it's like 4 months ago, but you can still use it. This allows us to see if there were any performance differences. It is important to note the differences between the pre-trained model of OpenAI API and the web interface of ChatGPT. So because these 2 things are different. So pre-trained models provide the OpenAI API, our standalone model without a user interface, require coding for integration. I want you to just know about this. And then we also experimenting with the base, few shots, and few shot train up the thoughts prompts for optimal performance. And then we also investigate the impact of the fine-tuning on the large language models. We use 90 essays for essay classifications, and then 90 essays for the writing quality. Yeah. So maybe you might not familiar with some LLM related terms. So let's review those terms first. Think of the prompts as the instructions you give an LLM to guide what it generates. So there are 2 main types: zero shots and few shots. Zero shot is the basic task descriptions without any examples, and few shot includes a few examples to help focus the LLM's response. and train of thought, which is COT, is a technique that encourage the ChatGPT or large language model to break down the complex problems into smaller, easier steps. This leads to more logical and accurate results. And the research shows that the few sharp prompts usually improve the large language models, ChatGPT performance improved, and then the combining few sharp prompts with the COT leads to even better outcomes. And then in this study, actually there is no pure zero approach, because to obtain a relevant scores to prompt for essay grading needs to include instructions and describing how to classify students' essay into 3 stances and assess them on a scale 1 to 7. So this comprehensive prompt terms the base prompt. And so evaluation metrics is really important to pairing how well different machine learning and the large language models perform in AES. For the quality of writing, we use metrics like RMSE and R squared. Lower RMSE and higher R squared indicates better model performance. And for essay classification, which is categorical outcome, we use metrics like accuracy, unweighted kappa, and the quadratic weighted kappa. So these measures agreement between the model generated classifications and human expert ratings, and higher values are better. So, and thank you for waiting for all the long explanation. Now let's focus on the interesting example, the result. So in terms of the prompting approach, we found that the base prompt consistently outperform few-shot learning approaches across all ChatGPT variations. And this is very clear in lower RMSE values, indicating less errors, and higher R-squared values, indicating a stronger relationship between ChatGPT scores and human rating. And adding train of thought prompting to the few shots learning doesn't consistently improve the result. In fact, we saw the mixed result. And then when it comes to the model version, an interesting trend emerges with the model version. In many cases, older models outperform newer ones, especially with the fine-tuning. And then focusing on the impact of the fine-tuning, the older version generally perform better the updated version. Surprisingly, the newer fine-tuned ChatGPT model shows performance similar to the non-fine-tuned model. Additionally, its few shots and few shot COT approaches result in very low R-squared values, often less than 0.1. And then all tree-based machine learning models using 80 to 20 trained test splits show the similar effectiveness in predicting writing quality, but the tree-based models consistently much better than the ChatGPT older result. So, except the ChatGPT with old ChatGPT with a fine-tuning model here. And then for the essay opinion classification, for prompting approaches and fine-tuning impact, few-shot COT prompts significantly improve classification performance, often achieving human-level agreement. The range is from 0.6 to 0.73. And then, however, the further fine-tuning does not consistently improve the accuracy with this prompting strategy. So base prompt achieve the highest accuracy in the fine-tuned ChatGPT model. And in terms of the ChatGPT versions, newer ChatGPT models generally outperform older version, especially newer model without fine-tuning offers the best combination of cost efficiency, and performance for essay classification. And then the focusing on the comparison between the ChatGPT versus machine learning, XGBoost was the best performing as machine learning model, but its UWK still falls behind most ChatGPT models. So except XGBoost, most ChatGPTs generally outperform traditional machine learning models in opinion classifications. So let's take a look the performance of our machine learning models for quality assessment. Just focus on the only the machine learning method. So RF and RRF perform similarly, especially with the smaller data set. GBM consistently outperform the other tree-based model for quality predictions, and XGBoost shows the weaker performance in this test. And then finally, let's examine how machine learning models perform in classifying essay opinions. Boosting methods are better compared to random forest method. And then GBM XGBoost shows similar performance until 60-40 splits. With the larger tracing sets, XGBoost becomes the top performer, and RF and RRF remains consistently similar across splits. Thank you for all the listening to all the results, and now let's go to the discussions. So this current study explored the potential both tree-based model, tree-based machine learning, and the large language models for AES. Our result for several valuable insights. LLM shows some potential for essay grading, particularly in the classification of essay opinion, where they generally outperform tree-based machine learning model. But when assessing essay quality, which is a continuous outcome, tree-based models outperform ChatGPT, and the previous research suggests the few-shot and chain-of-thoughts techniques improve ChatGPT's performance, but our study found mixed result. And then we also observed the fine-tuning and model of this can significantly impact the ChatGPT's performance, although the benefits of fine-tuning were not always consistent. And then the limitations, and then so performance of both large language models and machine learning models depends heavily on the factors like specific pre-trained model prompting techniques, and then the types of essay data used. So future studies should include broader comparison. So we need to test other models like Gemini and Llama, or experiments with the fine-tuning model on a neural ChatGPT or other models. And then we also need to use the diverse prompting strategies. And then we also use the essay from the grade 4th to 8th graders, but the next time we should use the essays from the diverse demographic. So the implications and simple prompting techniques are often sufficient when you do the automated essay scoring. When fine-tuning, outcomes vary depending on the model versions and examples you provide. So we should be careful when selecting examples for prompting and fine-tuning. Also, it is important to should be aware about this, and ChatGPT API results differ the web interface of ChatGPT. Considering all of this, while using LLMs and machine learning for AES to fully replace human grading still remains a distance fall. So these approaches hold great promise as a powerful tools to augment the grading process, but their susceptibility to biases and less transparent decision-making process necessitate the further research and development to ensure fairness and responsible implementations. So thank you for your attention, and this research provides some insight. But thank you for your listening to our research and your attention. And So if you have more questions, please reach, this email and this QR code. Thank you so much.
Thank you, Dr. Kim. Wonderful presentation. I really appreciate it. We have one question that popped up so far. And again, others, if you do have a question, again, you can use that Q&A button on the Zoom bar or type it in the chat. But the first question that came in was, I may have missed this. Have you tried fine-tuning the GPT 3.5 and what's the results?
Can you say one more time for me? Because we fine-tuned all the models we have.
Okay. Yeah, the question was,
GPT.
did you fine-tune the GPT 3.5 and what were the results?
So fine-tuning result was mixed, and then some, especially for the continuous outcome, fine-tuning doesn't work well. But for the categorical outcome, the fine-tuning model, fine-tuned ChatGPT was better than just non-fine-tuned model.
Thank you for that clarification.
Yes.
We still have another 4 more minutes before our next session pops up. Oh, here comes another question in the Q&A poll. May you give some examples on how you have labeled the examples for your few-shot training? And I'll copy that question in the chat.
Okay. So if I'm not sure if you're familiar with some like fusion model, and you need to provide first the how ChatGPT can provide. So just provide a prompt about how to grade this essay, and then give the just few examples for the few shots, and then provide essays, and then their like its classifications. So it's looks simple. If you just send me email, I can just send my prompt to you directly. It's not complex. Yeah.
Thank you. We have one that popped up, two that popped up in the chat. Actually, the first one is, would you be willing to share your presentation with some of the speakers? So the question came up. And the second question is, given humans themselves are subject to error, isn't the relevant question if the computer is better than the error-prone humans?
Wow, this is really interesting questions. While working on this project, we always talk about these issues, which one is better, and so that's why automated essay scoring. So we are using automated scoring, especially for the large number of the essays. So, so I don't have clear answers right now, but the current ChatGPT or the Gemini has some limitations, especially for the essay grading. So right now, maybe machine learning approaches, AES computer, maybe little better for the large number of the grading the large number of essays. But that's really good question. But that will be my future research, and I will focus more on this. Yeah. Thank you so much. Yeah.
Thank you, Dr. Kim. Wonderful job. Yeah, and for all the speakers, we'll be reaching out to see if we can get these slides. But Dr. Kim, there's also a request for the research paper. So I don't know if you want to share in the chat or send it to Allison and I. We can potentially collect those resources, maybe put them up on the website or send an email later.
So research paper is on, we submitted, but we are waiting for their reviewers' comments. And I can share the PDF file of my slide, but I cannot share the paper because still, I'm ready right now.
Perfect. Thank you. Well, I'm going to switch to the next session. And Dr. Kim, you have one more question in chat. Maybe you can answer it in chat while I introduce our next speaker. Our session number 2 of 3 is Juan Pinto from the University of Illinois at Urbana-Champaign. Thank you for going to share the screen. And again, you have the next 15 or so minutes to present, and we'll follow that with 10 minutes of questions like we did with this one. The floor is yours, Juan.
All right. Hello, everybody. Let me just hide my controls here. Okay. Hi. So I'm Juan Pinto, and I'll be presenting specifically on our ongoing work in explainable AI in education. And it's going to be kind of a high-level overview of some of the things that we've been working on, call to actions, and also opportunities for you to participate if you're interested in some coming opportunities that we've got. So here's the topics that I'll be hitting on today. I'll be talking a little bit about what it even means to have this challenge of interpretability, also presenting some preliminary work on creating interpretable AI models for education, and then also, like I said, talking a little bit about an upcoming opportunity for at a workshop. So this challenge of interpretability, first of all, interpretability is very important to transparency as a whole, which is a bigger kind of category. And it's important because it has implications for issues such as fairness, accountability, trustworthiness, and other issues that are very at the front of the public mentality when it comes to AI in education. There's all of these issues that you hear about, and transparency and interpretability as a part of transparency plays a big role in addressing these issues. And the reason for this is that a lot of AI models these days are what we call black box models, like this neural network diagram right here, which essentially just mean that they are very, very difficult to understand. Even if you have access to the model, even like open source models, open source LLMs that are very popular these days, just because you can see them, you have access to the parameters, doesn't mean that you can actually understand why they're making certain predictions. And there's two general approaches to this. And one of those is to try to make models that are intrinsically interpretable. And by that, I mean models where they're simple enough, usually, where we can understand just at face value what the parameters are doing on the inside. And that's this on the diagram, the bottom model here. You can tell it's transparent, so we can peer directly into it. Then there are also post hoc explainability approaches, which are really a family of analysis methods for trying to open up black box models. But the way that they work is that they're a little bit indirect. And so this top part of the diagram, you can see that the model itself, we don't have access to, or at least we can't understand what's on the inside. So in a post hoc approach, typically what we'll do is we'll create a simplified model that emulates what the more complex model does, but it's simple enough that we can understand it. But there are problems with this post hoc explainability family of methods. One of the biggest problems is that depending on the method that we choose to use can lead to different interpretations, different conclusions about how the model works, which obviously has problems for reliability and the validity of the explanation. And also, other authors have talked about additional problems, but the idea is that because the approach is treating the model blindly, it becomes a black box. And so we're not actually dealing directly with the model. We're using these proxy models, and there are additional problems that go into that. And I'm happy to talk about any of these points more in depth in the questions. I'm just going to kind of keep going for the sake of time. But these are the four main takeaways that we presented back in December at the TEL Summit in December, based on a review of the literature on XAI in education. The first one is that we feel like there should be more of a unified vision for XAI in education. There's a lot of talking past each other, a lot of using different terms to mean the same thing or similar things. We feel that there should be greater awareness within the field of education when it comes to the complexities of XAI, specifically the limitations of post hoc methods, which are often used indiscriminately. We also call for more research into possible approaches on how to create more interpretable models for education. And finally, also more research into how to evaluate the interpretability of a model. And so even if we have a model, how can we claim that it's interpretable unless we have robust methods for assessing that level of interpretability? And so I'll be touching on 3 of these points today. And so the first one is addressing takeaway number 3, which, just to remind you, is trying to create more interpretable models. And so this is just one of those approaches that we are pursuing in our lab currently. And this is the work that I'm pursuing for my dissertation as well currently. So the data that we're using for this comes from cognitive tutor algebra, which is an intelligent tutoring system. And it's a model of gaming the system behavior, which has been defined as attempting to succeed in an educational environment by exploiting properties of the system rather than by learning the material. So essentially, this is when a student is trying to cheat the system or trying to finish something even without actually going through the process of learning. Now, I'll just point out that the main takeaway here is not necessarily gaming the system, but it's more, we're just using this as an example of a model that we're trying to create that's more interpretable. But the method itself can be applied to any kind of model that follows this architecture. And the features that we're using for this model come from a paper by Paquette et al. From 2014, where they use cognitive task analysis to identify important variables that help identify this behavior among learners. And the approach that we're using to try and create it, try and make it more interpretable, is by essentially constraining the model itself to create more binary filters in the convolutional layer. So this is a convolutional neural network. You can see the architecture on the right here. It's a very simple model, trying to keep things relatively simple. But we are, like I said, constraining the convolutional layer by adding a loss term or a specific penalty term to the loss function of this model, so that as opposed to the filters that you see here on the right that are very, it's a continuous value, so it's very difficult to make sense of this grayscale image. Whereas on the left, these are binary values. And if you understand what the features are, then it's very easy to see, okay, at this point, the student engaged in these behaviors. And at this point, the student did not engage in these other behaviors. There's no middle ground, which follows the pattern of the actual features. So it makes it much easier to understand what's going on. And I will say with this model, this is very much still in the works. There are other approaches that we're using, or other constraining approaches that we're using to make it align even more with a human's understanding of the phenomenon, in this case, gaming the system. So the idea is there's a family of approaches where we can constrain the model in certain ways to make it fit better with our conception of the behavior, but at the same time allow for flexibility so that the neural network itself can learn the patterns that will make it accurate. And we've compared some accuracy and have found it to be as accurate as other models as well, but this is ongoing work that we will be presenting and publishing. There is some preliminary work that I've presented last year, and you can see the citation here for some more details on the model. For takeaway number 4, which is about evaluation methods, we do also have, as part of this project, where we are trying to evaluate the interpretability of this specific model by using a human-grounded evaluation approach, according to the Doshi and Velez and Kim taxonomy of evaluation methods, where we have human participants try and identify what the model will predict. This is called forward simulation. So we give them filters, the convolutional filters, and we ask them to identify what the model will predict. If it's accurate, then that's a good sign that this model is interpretable, as well as a counterfactual simulation, where essentially we again give them the data, we give them some filters, and we give them the output of the model, but we ask them to change one of the inputs so that the output will also change. And this is another way to kind of measure and see how well they actually understand how the model is working. In this case, the filters themselves, as you see them here on the right, are the form of explanation that we're using to for the participants to try and understand what the model is doing. And so we're using this as a way to say, yes, the model is interpretable, or it is not interpretable, or fall within that range somewhere. But that's just one possibility. And so beyond that, we're also trying to conceptualize a framework for evaluating explainability in AI, where we're looking at multiple different aspects of what it means for a model to be interpretable or for an explanation to be interpretable. And in this case, we are beginning, this is still very early work, but this is kind of the early stages of this framework where we are essentially saying, an explanation needs to be useful. And for it to be useful, it requires both intelligibility and faithfulness. Intelligibility refers to the fact that a human can actually understand what's going on by looking at this explanation. And faithfulness is this idea that the explanation is actually valid in terms of what the model is doing. Is it actually faithful to how the model actually works? You can have an explanation that's easy to understand, but it doesn't actually tell you anything about how the model works deep down, which is one of the problems with post-hoc explainability approaches. And for intelligibility, we believe that it needs to be, the explanation needs to be plausible for it to be intelligible. Whereas an explanation also needs to be stable, meaning that it's reliable across different instances and similar different inputs for it to be faithful. So this is just kind of trying to create a hierarchy so that we can start to understand how best to evaluate these different models and explainability approaches. And now for the takeaway number one, which is about increasing awareness and also creating this unified vision for XAI in education. We are hosting a workshop at upcoming EDM in Atlanta, but it's going to be hybrid. So for any that aren't going to be there in person, you're welcome to register. And the idea with this workshop is to bring together people who are interested in XAI in education and create this, like I said, this unified vision of, first of all, where are we at? What have we studied? What is working? What isn't? But then also, what are the gaps that we want to pursue in the near future as a research community? And we have organizers from UIUC, where I am, also EPFL in Switzerland, and the University of Mannheim in Germany. And the program committee involves researchers from all over the world. But you're welcome to access the website there for more information and to register at the EDM website. But essentially, these are just kind of some of the ways that we are pursuing our goals of creating more interpretable, more explainable models, and also to bring awareness to the field so that we can move towards a future where these models are easier to understand, so that way students, teachers, parents, administrators feel like they can actually trust these models more because they can hold there's more sense of accountability and more sense of fairness and understanding how they work. So thank you very much, and I'm happy to answer any questions.
Thank you, Juan. Wonderful. Yeah, the first question comes directly in the chat from Raj. It says, given the output of the LLM will differ even if the same prompt is provided across different sessions, do these methods work to provide explainability regardless of the variation of the output?
Yeah, that's a great question. So I will say we're not looking at an LLM right now with this specific project. This is a neural network. It's not a transformer architecture, which is usually how all LLMs at this point work. It's a different kind of architecture. So we're not doing this with LLMs, but this is a very, obviously, everybody's thinking about LLMs and generative AI at this point. And so we are definitely interested in pursuing this question of what does it look like when we're talking about an LLM? And one of the issues is the point that you just made is, yeah, the output differs, right? So this is not consistent. And it has to do with the way that the architecture of the model is set up. It has to do with the way that the model itself just functions. But this is not exactly what we are looking at the moment. But it is a really important question. I agree.
Great. Any other questions? Please feel free to submit them. You have some big thank yous already coming in. Here comes one from Allison. How much of a compromise would be tolerable in the model performance, e.g. accuracy, to increase its interpretability? Does it always lead to a loss in model performance?
Yeah, that's a great question. There is this idea that typically the more interpretable a model is, the less accurate it's going to be. This is definitely not across the board the case. I mean, the work that we just saw from the previous presenter showed, even though random forest is not exactly the most interpretable, it is in a way more interpretable than LLMs. But in some cases, it outperforms the LLMs at specific tasks. So there is definitely a trade-off, right? Which is why when we're talking about interpretability, it's important to account for this. In the model, the specific model that we've been looking at, this convolutional neural network, we created one that was not interpretable. So it was the same architecture, but without the penalty term in the loss function, essentially meaning that it's fully not interpretable, black box. And we compared the accuracy of that model to the one that we are trying to build that is interpretable. And we found the interpretable one to be slightly less accurate at the task. And so it really depends also on the context, the situation itself, right? In some cases, you might be willing to have a slightly less accurate model if you can understand it better, especially in high stakes domains such as education. This is often the case where if a model, no matter how accurate it is, even if it's not interpretable, it might not actually get used in schools and classrooms or whatever the context may be because it can't be understood. And so in some cases, in some scenarios, you'll want a model that is interpretable over one that is a little bit more accurate. But of course, the ideal is to have both.
Thank you. Still have a good couple more minutes here if anybody would like to submit any other questions.
I see a question in the chat here from Arun. I submitted a paper to the workshop where the acceptance rejection results already communicated. They have not been. We are just getting the final reviews from the reviewers. So as soon as we have those, then we will communicate the final acceptances. I will say, unless there's other questions, back to the first question by Raj about LLMs, one of the things that we've been thinking about is because LLMs are notoriously very difficult to understand, and there has been some early work to try and understand them. I know there's been some recent papers from OpenAI and others as well on this topic, but it seems like this is going to take some time to be able to fully understand if we're ever able to do it. But one idea and one potential is to have both, right? So you have both an LLM and other kinds of models that are easier to understand, performing different functions within this larger educational system. So for example, in an intelligent tutoring system, you'll typically have a learner model that tries to keep track of students' levels of knowledge, as well as non-cognitive skills and affects, so different emotions that they're feeling. And one possibility is to incorporate all of that within a single LLM that the student interacts with. But because of the lack of interpretability, another approach would be to have a dedicated learner model that is interpretable, that communicates with the LLM as a separate layer. And you can imagine multiple different kinds of models serving different tasks, depending on the need for interpretability. And the LLM can serve as this kind of student-facing or this front-facing layer of the bigger system of the architecture that simply is there to communicate in a natural language. So that's one possible way to address this issue with LLMs.
Yeah, that last comment you made me think about the role LLMs can help translate some of the results into easier ways for educators to understand as well.
Yeah, so I'm not sure if this is what you're getting at, but this is also another potential area of interest where LLMs can serve to make things more interpretable. So essentially the LLM acts as the layer providing an explanation, which is a little bit different than what I was talking about earlier. But in this case, the LLM could be fed, let's say, the internal parameters of a specific model, whatever it may be, and we can ask it to try and make sense of this. You do still, because the LLM itself is not interpretable, do still encounter the problem of, okay, well, can we trust the LLM's interpretation of the model? So in essence, this is kind of like another post hoc approach, but at least the LLM does have access to the internal parameters, which typically post hoc approaches don't. They're just looking at inputs and outputs. But it is definitely another possible area of research there.
Comment or a question here. Can we also get more resources for LLM with a center focus for the student? Might lead to more knowledge interest areas.
Not sure I understand the question.
Colin, maybe you can add another clarification to that, or feel free to unmute. We could let you ask that question. Arun's helping. I think they're asking for recent papers on LLM in the education that focus on student learning.
I mean, there's a lot in the LLM space at the moment. One area that you might be interested in is also, I mentioned this workshop on XAI in education. There is also at the same conference, at the Educational Data Mining Conference in July, ADM, there is going to be another workshop specifically on LLMs in education. And so that might be an area where you can get kind of the latest research in that area. Yeah, thanks everyone for helping there in the chat as well.
All right. Just give another minute or so to see if any final questions come in. Okay, well, feel free to continue to send those questions in the chat, and I know Juan will be sticking around for a little bit, and he could answer those as well directly in the chat. And thank you, Young Juan. I see you're also continuing to answer those questions as well. All right, for our final and third presenter, I'm going to introduce you to Thomas Joyce, a recent undergraduate graduate of Notre Dame, and he'll be giving his presentation.
Thank you. Good afternoon, everyone. So today I will be presenting on early grade prediction and validation to support students in the foundational STEM course. And I would like to thank my advisors at the University of Notre Dame for collaborating with me on this project. So our research falls under the broader field of learning analytics, which uses tools from AI and data science to really help us unpack student learning and optimize the overall student learning experience. Learning analytics data comes in many forms, some of which you're probably familiar with, such as grade histories from learning management systems like Canvas, clickstream data from online learning platforms, and even student survey data from assessment wrappers. Some of the key goals of learning analytics are to provide personalized and timely learning feedback to students. We'd also like to help instructors track student performance so that they can improve their own teaching strategies. And as we'll discuss more today, to use early grade prediction to identify at-risk students. So by predicting students' final course grades early in the semester, we can help instructors identify students who are at risk of failing or dropping out of the course. And that way the instructors can implement learning interventions to support those students. We often use very limited data to make these early grade predictions, such as the first few homework or quiz scores. And the outcome variable is typically binary, so whether or not the student passed or failed the course. A lot of recent work has employed machine learning methods to accurately predict students' academic grades early on in the course. And the most common approach is to compare different machine learning methods, such as logistic regression or gradient boosting, to see which ones are the best at identifying at-risk students. However, there's a lot less emphasis on the validation of model performance, so that's something that we will try to examine in our research. So in early grade prediction, fairness is very important. We do not want our models to be biased against specific student groups. And this raises the question of whether demographic variables should be included as predictors in our models. One of the main arguments for using demographic data as predictors is that it can lead to more accurate predictions of at-risk students. And sometimes this may be true, but there's a lot of other factors to consider. So those who argue against using demographic data as predictors say that it could suppress more actionable variables. And this might occur when there's confounded between a demographic variable and some other predictor of interest. It could also reinforce biases that are already present in the training labels, which could be harmful to historically underrepresented groups. And another perspective is fairness through unawareness, which says that an algorithm is fair if it does not see those protected attributes in the decision-making process. So instead of using demographic data as predictors, we'd be better off as using that to evaluate the fairness of our models. And between these two perspectives, there's a middle ground, which is to use demographic variables to apply fairness constraints in the model without explicitly including those as predictors. So with that background information in mind, I'll go ahead and introduce our study, Early Grade Prediction and Validation to Support Students in a Foundational STEM Course. So let's break this down into 3 parts. The first is STEM course. We're specifically looking at an organic chemistry course at a mid-sized private university. Early grade predictions. We would like to predict students' final performance groups before the midterm break. We do not use demographic data as predictors because we simply did not have access to this. And validation. We use the spring 2023 course data to train our predictive models, and now we'd like to test our models on the spring 2024 data. And validation is very important if instructors want to actually use our models to identify at-risk students and deliver some of those learning interventions. So previously, we created ordinal forest models to predict students' final performance groups before the midterm break in spring 2023. And on the right side here, you can see that we achieved an overall accuracy of about 85% by week 7 of the course. So now our question is, will these results hold when we test the models on the spring 2024 data? So before I get more into the methods and results, I want to give a more context about the course. So our study focuses on the first course of a 2-semester sequence in organic chemistry for science students. And most of the science students take this course in the spring semester of their first year. The course meets 3 times per week for a lecture. And there's also a separate tutorial section that meets once per week for additional problem-solving practice. Both of the semesters had a total enrollment of about 400 students. And our main data source for this study was the Canvas gradebook, which had all of the assignment scores for each student. So as for the overall grading scheme, there were 4 different assessments. So these were 10 weekly Canvas quizzes, 13 tutorial problem sets, 4 midterm exams, and a cumulative final exam. One important thing to note here is that students had 2 identical attempts on each of the Canvas quizzes, and only the highest score was accepted towards their final grade. So we can see in the table on the left, the weights for each assignment were pretty similar between the spring 2023 and spring 2024 semester. On the right side, we have the letter grade by final percentage. So students who had a final course grade percentage between 90 and 100 had a letter grade of A in the course, 86 to 89 was A-, and so on. So essentially what we would like to do is use early assessments on the left table to predict the grades on the right table. So after discussion with course instructors, we divided students into 3 performance groups based on their final course grades. And these were thriving, which is between 86 and 100%, succeeding, which is between 70 and 86%, and developing, which is below 70%. The reason we use 3 performance groups instead of the traditional pass and fail performance groups is because we wanted to provide some more fine-grained insights for the instructors at different levels of student learning. And we can see that the distribution of performance groups was pretty similar between the spring 2023 and spring 2024 semesters. The thriving group always had the most students. And really what we're trying to do is use assessments from early on in the course to predict the final performance group. So in other words, the performance group is the dependent variable in our study. So this tree diagram shows the overall structure of the course. You can see that there were 17 weeks with spring break occurring in week 9, and each week had some combination of tutorial problem sets, quizzes, and exams. We would like to use these assessments in the first 7 weeks to predict the final performance group. One thing to note is we didn't include the tutorial scores as predictors because these were graded based on completion, and so almost all the students scored 100% on the tutorials. So this slide shows the quiz scores for both semesters. So students had 2 attempts on each of the quiz. We have the first attempt scores on the top and the final attempt quiz scores on the bottom. You can see there was a lot more variation on those first attempt scores. So we decided to use the first attempt scores as predictors in our models. This slide shows the exam score distributions for both semesters, and you can see it was pretty similar across the board. We just used exam 1 and exam 2 as predictors in our models, and that was because those exams occurred before the midterm break, and we wanted to obtain the grade predictions as early as possible. So our study was guided by 2 main research questions. The first one is it possible to create models that accurately predict students' final performance groups at early course stages without using demographic variables? And as I showed earlier, we achieved about 85% accuracy in the spring 2023 course by week 7. So now the question that we're focused on more is number 2, which is, can we replicate the spring 2023 predictive model results in spring 2024? So as for the methods, we used ordinal forest models to predict the final performance groups in weeks 3 through 7. And the ordinal forest is a random forest-based method specifically designed for an ordinal response variable, which was very important in our case because thriving and succeeding and developing are 3 ordinal levels. As I mentioned, the predictors in our models were all the first attempt quiz scores and exam scores leading up to the specific week. So what this means is that week 3 had the fewest number of predictors, and week 7 had the most predictors because there was more assignments at that stage of the course. We did a 70-30 split for the training and test set using the spring 2023 data, and we balanced the training data using synthetic minority oversampling technique. We used the ordinal forest package in R for training, and now really our goal is to test those spring 2023 models on the spring 2024 data. So we had 3 main model evaluation metrics. The first is just the overall accuracy. So we wanted to see how well the classification models performed overall on each of the 3 performance groups. The second was a quadratic weighted kappa. So this kappa is a measure of agreement between the predictions and true labels. And we use quadratic weights to give a larger penalty for predictions that are far from the true class value. So for example, if a student was truly thriving, but the model classified that student as developing, that would have a larger penalty towards the kappa score. And kappa follows a scale where 0.01 to 0.2 is slight agreement, 0.21 to 0.4 is fair agreement, and values close to 1 represent an almost perfect agreement between the raters. And lastly, we examined the non-thriving sensitivity, which is the proportion of non-thriving students that were correctly classified as non-thriving. So in our case, if a student was not thriving, that means the student was in the succeeding or developing groups. And we can assume that the non-thriving students are more likely to be at risk of failing or dropping out of the course. So it's important for us to maximize the non-thriving sensitivity. So now I will get into the classification model results for weeks 3 through 7, and we'll also compare the spring 2023 performance to spring 2024. So this is the model results at week 3. Here you can see the performance group was predicted by quiz 1 and quiz 2. We have the spring 2023 model performance on the left and the spring 2024 model performance on the right. And down here we have the confusion matrices for both semesters. So the true performance group label is on the horizontal axis. The prediction from the model is on the vertical axis. And everything that's on the diagonal is a correct classification. It's important to note that there were fewer observations in the spring 2023 confusion matrix compared to spring 2024. And that's just because we only used 30% of the spring 2023 data for testing our models. So here we can see that the overall accuracy was about 50% for both semesters. The weighted kappa score suggested a fair agreement between the predictions and true labels, and the non-thriving sensitivity was only around 55% at week 3. Moving on to weeks 4 and 5, here quiz 3 and exam 1 were added as predictors in our model, and the model performance improved substantially compared to week 3. So the accuracy for both semesters was between 70 and 75%. The quadratic weighted kappa score suggested a substantial agreement between the true and predicted labels. One difference, though, was that the non-thriving sensitivity was a lot higher in spring 2023 compared to in spring 2024. And as you can see in the confusion matrix on the right, there were 71 students in the succeeding group in spring 2023, but the model classified them as thriving. So these were misclassifications. Now in week 6, quiz 4 was added as a new predictor to the models. And here the performance was quite similar to weeks 4 and 5. Again, we had an accuracy between 70 and 75%, a quadratic weighted kappa around 0.7, and the non-thriving sensitivity was still a bit higher for spring 2023 compared to spring 2024. And lastly, in week 7, quiz 5 and exam 2 were added as predictors in our models. And here, spring 2023 had a very, very good performance. So the accuracy was close to 85%. The quadratic weighted kappa suggested an excellent agreement between the two raters, and the non-thriving sensitivity was around 88%. However, the model performance wasn't quite as good in spring 2024. You can see the accuracy was only 77% here. Quadratic weighted kappa was around 0.73. And again, the model wasn't capturing all of the non-thriving students. We can see that there were 59 students in the succeeding group in spring 2024 that were actually classified as thriving by the model. So to summarize our results, we saw that in spring 2023, the accuracy increased each week. We had pretty good predictions by week 4. We had about 85% accuracy by week 7. When we tested those spring 2023 models on the spring 2024 data set, we had a similar overall accuracy and quadratic weighted kappa in weeks 4 through 7, but there was a lower non-thriving sensitivity, which is a bit concerning if instructors want to use our models to identify at-risk students. But overall, we can say we had satisfactory early grade predictions without using any demographic data. We only used early quiz and exam scores to predict that final performance group. And as we saw, the results were almost replicable in the spring 2024 semester, but it could be better if we increase that non-thriving sensitivity. So another thing to note here is our study follows an approach that's very similar to training, testing, and cross-validation and traditional machine learning, where we use 70% of the spring 2023 data for training. The other 30% was basically a holdout cross-validation set, and we used all of the spring 2024 data for testing our models. However, I'll note that one potential point for improvement is to use a stratified train test split on the spring 2023 data to preserve the original performance group distributions in the training and test set. And I'll get into that a little further on the next slide. So this slide shows the percentage of students in each performance group. On the top left, we have the entire course for spring 2023, and this was split into a training set and a test set. And you can see that the percent of students in each performance group was a little bit different between the training set and the test set, and that's because we did not do a train test split with stratification. And this could have, even though we balanced the training data, using SMOTE, it still could have negatively impacted the model performance on spring 2024. So we're thinking in the future, if we do that train test split with stratification to balance the percentage of students in each of the performance groups, then we might be able to achieve a higher non-thriving sensitivity. And this would also lead to more reliable model performance statistics when we test the models on spring 2024. So that's something that we'll try to do in the future. And as I started mentioning, for the future directions, we'd like to also explore some other machine learning methods, such as gradient boosting, and see how they compare to ordinal forest. We would also like to continue to test and refine our models, even using the spring 2025 data. So the eventual hope is that instructors can use our models to identify at-risk students and deliver some learning interventions. Previously, we did some work on item analysis and provided this information to instructors, So this really is used to compare the performance groups on specific exam topics and questions. And instructors are able to get some more detailed insights from that. So we hope to continue the item analysis work in the future. And lastly, assessment wrappers. So these are short post-exam reflection surveys that ask students a lot of questions about how they prepared for the exam. We would really like to use the wrapper data to evaluate the individual fairness of our models. And I'll discuss this a little bit further on the next slide. So how can we use the assessment wrappers? So these are short surveys given after the exam, and you can see students are asked a series of questions about their preparation, confidence, study time, and study strategies. These were implemented after 2 of the midterms exams in spring 2023 and all of the midterm exams in spring 2024. And so far, we've analyzed a lot of this data and generated some descriptive statistics for the course instructors. So over here, you can see we have the overall exam 1 study time, and down here is the overall exam 1 study strategies. In terms of the individual fairness evaluations, what we're hoping to do is see if students who had similar responses to the wrappers had received similar grade predictions from the models. One concern here is that the wrapper response rates were only around 70%, so we might not have enough data to conduct all those individual fairness evaluations. And these are our references. So I'd just like to thank everyone for attending today and listening to my presentation. It was a real honor to be able to present at the Tail Summer Symposium. With that, I'd be happy to answer any of your questions. Thank you.
Thank you, Thomas. We have 2 questions, one in the Q&A and one on the chat. We'll do the one in the chat first from Arun. It's not clear why we are predicting week by week. Wouldn't it make the model predictions weaker, or is it developing on the weights learned from previous weeks?
Yeah, so let me go back to this slide here. The idea is by predicting week by week, since we're only using the predictors leading up to that specific week, at each week we'll have more predictor variables in our model, which should improve the performance. So for example, in week 3, only the first and second quizzes were used in our models because there were no other assignments up until that point in the course. But in weeks 4 and 5, we added quiz 3 and exam 1 as predictors. And by the time we get to week 7, quiz 5 and exam 2 were added as predictors. So with more assignments, we should be able to obtain a better grade prediction.
I'm copying and pasting the question that came in from the Q&A from Eric. While you mentioned that the tutorial assessments were largely assessed as complete or incomplete, was student accuracy evaluated? If so, was any consideration given to including performance scores of tutorial assessments in the model?
That's a great question.
Actual grade.
So these were the tutorial scores for both of the semesters. And as I mentioned, there's 13 tutorial assignments. And you can see that almost like 99% of the students scored 100% on these assignments since they're graded based on completion. So that's why we opted not to use those, because we did not think it would help to differentiate students. But that is something we could potentially explore more in the future, like seeing, maybe even using it as like a binary variable, just to see like whether it improves the model performance.
Great. I think Arun has a question about SMOTE. Your methodology with SMOTE works well for balancing, but the issue can become unrealistic. Can you talk a little bit about that?
I'm sorry, I didn't quite hear the very end of that.
Sure. It says, maybe it's more of a comment. SMOTE works well for balancing, but the issue is it become unrealistic. Maybe you can talk a little bit about your methodology of using the SMOTE.
Yeah, so with that, let me go to the this slide. So our hope with using SMOTE was to generate synthetic samples in the succeeding and developing groups so that they would reach the same size as the thriving group. So there's 161 students in the thriving group in the training set. And when we use SMOTE, we were able to have the same, we also had 161 students in the succeeding and developing groups. But that's a good point. We could also explore other balancing techniques in the future. And another thing that I was talking about earlier is we could also do that train test split with stratification to preserve those preserve the proportions of students in each performance group. So yeah.
This is a follow-up from Eric's question about the tutorials. I was wondering if the instructors had evaluated those questions, even if they gave full points. I think did you cover that?
Yeah, so they were graded solely based on completion. And the way the course works is that tutorial section meets totally separately from the lectures. It's like graded by the TAs. And so if a student shows up to tutorial and they have their problem set done, they get 100%. So I don't think the questions are evaluated by the instructors. Yeah.
We have another question in the chat. So what happens for the students that opt to do the texts in the last 2 weeks, which fits the outliers of student data recorded? How would you approach that? Is that question making sense to you, or do we?
I'm sorry, could you repeat? Yeah, that I'm not sure exactly if it.
Yeah, I'll put it at the bottom of the chat for you.
Okay.
But it says, why you mentioned that, oh, that's the wrong one, sorry. Well, we got a couple questions coming in here. Here. So what happens for the students that opt to do the texts in the last 2 weeks, which fits the outliers of the student data recorded? How would you approach that? Do we need more clarification on that?
Yeah, I'm just not sure what means by the outliers, but the last two, sorry about that. Yeah.
Yeah, Carlo, if you could maybe rephrase that, maybe give more clarification to that question. I'm going to jump to the next one in the chat. Did you include the quiz questions themselves into your analysis from semester to semester? Are the questions the same or are they different? If they are different, will they affect the results?
That's a really good question. So when I had the data set, the exact quiz questions weren't included in that. So I'm really not sure whether they were different between the semesters. I'm assuming there could have been some slight differences because I know from semester to semester, the instructors may tweak certain questions, but that would be something interesting to explore more in the future.
Okay, we have another question in the chat. One asks regarding SMOTE, as long as the model performs well on unseen test data, the SMOTE is helping us as expected, but it is worth trying other data balancing approaches to compare.
Yeah, thank you. That's really helpful. I think, as I mentioned earlier, that's probably something that we'll look to explore more in the future, like different balancing approaches. But we also, we mainly just use SMOTE. We've also looked at just general like random oversampling of the minority groups using sampling with replacement. But there's other balancing approaches that I definitely would explore in the future. Yeah.
Great. Give another moment or so to see if any other questions come in. And we do have another 2-3 minutes before we wrap it up. If there was other questions we wanted to go back to as well from the previous sessions, we do have a couple extra minutes here. So feel free to send in any final questions, and I'll pass it over to Allison to wrap this up. Or a question you might want to ask across 3 presenters.
Yeah, well, thanks everyone. First of all, I want to say thank you to our 3 presenters, wonderful presentations on very different topics, but all very engaging, and congratulations on doing such nice work. Second of all, I want to say thank you to our audience. Great questions asked, generated a lot of thought-provoking discussions. Thank you all very much. And lastly, I want to say thank you to Alex, who did a wonderful job coordinating the questions and answers. Before we close, I just wanted to bring your attention to the online symposium website. So this session, this symposium, is recorded. So as we have the videos available, we will post updates to the website And I put the link again in the chat box so that you can access the video. And if we have other information to share, for example, slides or research papers, we will also post them on the website. I also wanted to say that we plan to hold symposiums down the road. I saw a question earlier about how to get in touch if we want to present at the symposium. Again, more information is probably going to be posted on the symposium website. So do check for updates. And for all who registered, we have your email addresses when you register. So we will also be sending out notification emails when we have updates to that email address when you register. And with that, I want to say thanks everyone again. It was great seeing everyone. It was great to see such enthusiasm and passion for AI in education work. And I wish you a wonderful summer. And we will be in touch again, like I said, with updates. So thanks, everyone. Enjoy the summer.
Thank you, everybody.
Bye.
Thank you, everybody.